recording. Yes.
Well, good morning or good afternoon or good evening to everybody. And now we have pleasure. I have the real pleasure to introduce a good friend and a wonderful professor, a very distinguished scientist, is Professor Anbarasan. He is from the Center of New and Renewable Energy Studies, Department of Physics, Periyar University, Periyar Takalai Nagar, Salem, in Tamil Nadu, India. He's going to talk about the role of man-made metamaterials in nano optics, from fiction to fact. I had to say to Professor Anbarasan how happy we are and how grateful we are to him because of all his effort to help us. Um, well, we're doing the best we can, and thank to God and to the Lord, we have friends which are coming along with us. So, Professor, you are more than welcome, and please, you can start. And let me say that I'm going to mute, so there will be no noise from this end. Okay? Take your time and very good luck, and thank you once again.
Thank you very much for your nice introduction, Professor. This is my greetings to all who joined in this virtual webinar, which is entitled on role of man-made metamaterials in nano optics from fiction to fact. So in this way, my talk charted out in this way, like what is nano optics and its applications, then introduction to metaphysics and the metamaterials, then classification of different types of metamaterials, then plasmonic metamaterials, theory and experimental analysis involved in this talk, and how theoretical approach based on our own licensed software ZMax. Using this computational methods, we have also comparatively studied the behavior of different types of plasmonic metamaterials and how it is useful for our main applications towards how to protect the earthquake, how we can protect the seismic waves by the way of fabricating the metamaterials around the building or any other uh, systems to be protected. So finally, I will cover that conclusions. So in this way, nano optics is nothing but the study of behavior of light, particularly in the sub-wavelength. It is meant that nanometer scale, under that interaction of this sub-wavelength scale object with the light. And also it covers the branches like optics, optical engineering, electrical engineering, and also nanotechnology. The nano optics often involves dielectric structures such as nano antennas or metallic components which can transport and focus light via surface plasma polaritrons. Before understanding the subject nano optics, some of the basic concepts involved which are more important to identify the nano subject is how we can reduce the spot size without any diffraction is our aim and objectives of our nano optics subject. Here, when you are talking about the components like lenses, microscopes, and other precision instruments involved focused light. This focused light spot must be in the deep subwavelength scales. Only because of this narrowed, fine-tuned spot size can be used for many applications. So for that, we have to shape the tightly focused light, particularly the laser light, in terms of Bessel beam. Is meant that diffraction-free beam, that is called Bessel beam. So it is also possible to fuse the light into subwavelength, that is nearer to the wavelength of or fraction of the light used. So for example, surface plasmons, localized surface plasmons around nanoscale metal objects, and also many applications like making the nanoscale sharp tips used in near field scanning optical microscopy, that means NCHOP, and also photo assisted scanning tunneling microscope. Here, the application is varied from our day-to-day requirement. So in this way, the Nano Optics researchers doing variety of experiments to achieve the goals in the field ranging from biochemistry to electrical engineering to carbon-free energy. So a few of the goals are summarized one by one here. Here, our applications also involved that optoelectronics and microelectronics. Suppose if you are considering a light which is squeezed into small volume, so it can be observed and detected by a small detector. So for that, many integrated circuits can be made by photolithography. It is essentially important that the light needs to be extremely sharpened images. Even in the case of miniaturization of transistors, the sharp images are required to integrate the imported light along with the speed in that systems, and also that the reducing the cost of the manufactured optoelectronic devices. So in this case, many optoelectronics communications using the microchips via waves also possibles, that is waveguides also possibles. Even in the solar cells, it is also used, like how we can using the nano optics technique, the intensity of light in the optimal location within the solar cell for trapping more light, it is possible. For that, we need to understand the band gap between the conduction and the valence bond. So it is also engineered in such a way that the intensity of optimal location can be identified for trapping of more light or conversion of light into electricity. Even the controlled release of anti-cancer therapeutics also used the nano optics. Even in the many surgeries are doing using that nano optical systems. Even in the spectroscopy also, surface enhanced Raman scattering using that non-linear optics also play the important role of nano optics. Apart from that, in the case of microscopy, when you are talking about many lenses are diffractive in nature, when you are preparing or fabricator or designed the lens like a super lens, we can use it for microscopy or identifying the nanostructures. So this is the very important one. We can go for high resolution for getting that smaller wavelength of light. So it involves raster scanning of very sharp tip or very small aperture over a surface to be scanned. That is the technique using the application of nano optics. Apart from that, higher hole mobility for lower charge recombination also possible into even in the case of silicon nanophotonics or plasmons, even the metal optics. So these are all the important applications of nano optics research. Our title is given how that metamaterial is used in the nano optics applications. That is our title of work. So for understanding from that, knowingly identifying that without those who are having any basic knowledge about metamaterials, we can easily explain that the meta means nothing but beyond, beyond, like physics is nothing but study of nature or natural phenomena. Metaphysics means beyond physics. It is meant that the nature of existence, the study of truth and knowledge, both are invisible. The truth and knowledge cannot be visualized. So like that, we, the experimentalists, we expect anything to be visualized or physically characterized. But in the case of metaphysics, it is the study of truth and knowledge. So like that, the meta material also is beyond materials. That is meant that artificially fabricated materials. That meta means changed or higher or beyond or altered from the nature. So they are called metamaterial because it existing only a small subset of electromagnetic properties, which is also theoretically available very broadly, but experimentally now after 1960 only they have started to go for fabricating or assembling or manufacturing this kind of metamaterials. So it can achieve negative index of refraction. That is the important point to be identified in this case of metamaterial is negative index of refraction. It is mean that zero index of refraction. Refractive index is nothing but it can be defined. The ratio that is the refractive index of the material medium can be defined as the ratio between the velocity of light in vacuum to the velocity of light in the medium. So in this way that the values must be negative. How far it is possible? Only because of the artificially fabricated materials like magnetism, optical frequency that also played an important role in the metamaterial subjects. Then plasmonics, it is also a very interesting field of optics occurring at the interfaces to metals where light induces collective electron excitations called plasmons. So in this case, plasmonic metamaterials is a metamaterial that uses surface plasmon to achieve optical properties are not seen in nature. So here the plasmons are produced from interaction of light with the metal dielectric materials. Even though it is a insulated, some for that classification within the range of some Zemans, it is classified dielectric materials. So under these conditions, the incident light couples with the surface plasmons to create self-sustaining propagating electromagnetic waves known as surface plasmon polaritons, SPPs. Once launched, the SPPs ripple along the metallic dielectric surface compared with the incident light. The surface plasmon polariton can be much shorter than the wavelength of light used. So nano Plasmonics also a important role with that young topic of research, which is part of nano optics. It concerns to investigation of electron oscillations in metallic nanostructures and nanoparticles. So surface plasmons have optical properties which are very interesting. One by slide we can discuss. Many animations are available in my talk. So it is very easy to understand that how the metamaterials are identified. For that, we need to understanding the Maxwell's equation. Del cross B equal to mu naught into J plus epsilon naught dou E by dou T. So these are all the things we know very well in the Maxwell's equations. This is the current density. This is the cross product, means the induced magnetic flux density vector. These two factors are important. That is magnetic permeability of space and electric permittivity of space. Mu naught and epsilon naught playing the major role in this way. So here the dipole radiation of dipole vertically in the page showing that the electric field strength. This is the color, blue color, and pointing vector in the order book. That is pointing vector is nothing but S equal to E cross H. This is electric field, this is magnetic field. So when you are talking about the electromagnetic radiation, the vibrating electric and the magnetic vectors in the perpendicular direction making into the direction of propagation. That is S, which is denoted by S. So for that, we need some basic ideas about why we need to understand about permittivity and permeability. So it is nothing but the property of material resistant to the production of electric field is measured in this way. That is called permittivity. So which can be measured in farad per meter. And also its value is 8.85 into 10 power minus 12 farad per meter. So it is mainly the principle involved is for the preparation of polarization of electric charges. Similarly, in the this is the electric field oriented one. This one is permeability is nothing but it is measured of how far magnetic field lines can penetrate a substance. It is also the property of permeability. So it is measured by Henry per meter. Its values is 4 pi into 10 power minus 7 Henry per meter. So it is used in capacitors like in the case of charges involved by electric charges. Here it is used for inductors. The application oriented is here inductors. So these are all the ability to understand that what is the permittivity and the permeability. So then we go to our local things which are happening. You see that for understanding that how that he is throwing one name is called Valerie in our local language. So he is throwing from that limbs. There are several ways of throwing and aiming. So how again it is reached to his hand. That is the important factors involving what are the spinning method is going to understand important. So it is aimed to for having revenge towards the enemies. It is used in our traditional period. For that, we need to understand that what is Valerie. How, with the based on that, I am going to explain what is how that metamaterial behaving. Later slides will show you the explanation clearly. So this is also one type of herb available in India that is called Garuda Sanjeevani. It is a herb which travels against the direction of water. The water is flowing this direction. This helical shape Sanjeevani is that is reverse directions it is going. Only because of the man-made material is possible. You see that he is pouring some water in that utensil, when it is flowing against that water flowing directions, it is moving upward. So this is the things how the meta materials behaves in its character. So for that, understanding that how to achieve negative index of refractions. So when we are talking about N is the refractive index, it is mu r is the relative permeability and epsilon r is relative permittivity. When you are taking this product root, it gives that refractive index of the material medium. So for that, we need to understand that the exponential of minus j pi into e power minus j pi whole things, we get that negative values. Though theoretically, we can explain in the simple way that these cannot occur simultaneously, but we can go for some particular region of frequencies, it is achieved by the some noble metals. So the resonant ferromagnetic systems display negative mu r at resonance. So what kind of structures it causes the frequency variation of mu r and epsilon r at atomic scale could be replicated on a larger scale. To appear homogeneous, the structures would have to be electrically small and spaced electrically close. This concept of metamaterial was first given in the microwave wave regions by Professor Sir John Pentry, father of metamaterials, recently, and also that the theoretical idea is given by in the year 1969-67 by B.G. Veselago from Moscow Institute of Physics and Technology, considered the theoretical model of medium known as metamaterials. This Veselago is the father of metamaterial theoretically, given that concept of negative index of diffraction. So for that, the different types of electromagnetic composite media, such as double negative material, you see that first quadrant, when you are drawing like that, dividing like 4 quadrant, this one is first quadrant, second quadrant, third quadrant, fourth quadrants. So when that epsilon greater than 0, mu greater than 0, it is nothing but it is called positive materials. So that the pointing vector will move forward. So similarly, when you are talking about epsilon is greater than, mu is less than, that is called mu negative materials, or it can be produced by some magnetic materials like ferrites. It is also called magnetic plasmas. Similarly, this is called electric plasmas. This is magnetic plasmas because mu is less than 0. Here, epsilon is less than 0. So that it is called electric plasma. This is called magnetic plasma. So this is called metamaterial behavior. Both are less than 0, epsilon and mu. So it is called double negative metamaterials. You see the pointing vector H and it is electric and magnetic vector perpendicular to the direction of propagation. But in the case of backward propagation, saying that pointing vector in the opposite direction, this is called double negative metamaterial. Even in the another slides will also easily explain that what is epsilon negative materials. This is called electrical plasmas. This is called magnetic plasmas. This is mu negative materials. This is double positive. This is double negative. This is both are greater than. This is both are less than of permittivity and permeability. This one is both are reverse like that. Epsilon less than 0, mu greater than 0. This is epsilon greater than 0, mu less than 0. This is also called gyrotropic magnetic material or plasma magnetic materials. This is electric plasma magnetic materials. Even in the other slide also easily explained that this is the pointing vector S in between that electric and the magnetic field vectors. This is the K vector. So everything in the forwarding direction, the propagation of waves in this direction only. But in the case of negative double negative materials, this is electric field, this is magnetic field, perpendicular to each other both. This is the wave vector direction, this is pointing vector direction. So totally reversing directions. What some animation showing that this is the important role playing in that negative index metamaterials. So I have also given some text to a understanding of double positive materials. So these are all the dielectric materials. The first quadrant saying that it falls under the category of dielectrics. It is the most naturally occurring the first quadrant. The second quadrant is epsilon negative materials. So this is nothing but it is noble metals like silver, gold. It behaves in this manner, particularly in the infrared and visible frequency domains. In the case of double negative material, that the third quadrant is called metamaterials. Both are less than 0. The fourth quadrant is mu negative materials are also possible. This category is gives some gyrotropic, means the rotationally having its properties. It exhibits the characteristics, and artificial materials have also been constructed by double positives, epsilon negative and mu positive properties. So here the theoretical explanation for understanding that double negative metamaterials. See here there are two equations, root of epsilon and the root of mu. So when you are expressing in terms of this one, finally this our series reduced in such a way that like that. This is for epsilon negative metamaterial equations. So this is also for mu negative metamaterials. For understanding or preparation or fabricating or assembling this metamaterial, we need to understand what is these two. So these are all called resonators. Resonators, or we can also call split ring resonator. That is ring type, this is square type resonators. So these are all the man-made material to our requirement of many applications. So this is, so in this introduction, so the successful implementation of metamaterial technology, particularly in the microwave spectrum, inherent difficulties existing for fabricating optical metamaterials. So most of the work today related to modeling and proposed designs. And day by day, they have the scientists, the scientific community developed many split rings, that is array of assemblies of many metamaterials prepared, fabricated in day by day. So these assemblies of multiple elements fashioned from composite materials such as metals and plastics. So these materials are usually arranged in repeating patterns at scales that are smaller than the wavelength of light used. So metamaterials derive the properties not from the properties of base materials. That is the important point. It is not based on its chemical structure or chemical reactions. It is only because of the newly designed structure. So their precise shape, geometry, size, orientation, and arrangement gives them their smart properties. It can also be manipulating electromagnetic waves. So by blocking, it means we can hide the image or the objects, like how that the magicians are doing. So using that metamaterials, we can go for what is called, that is clocking, cloking, clocking. So this also we can use it, bending of electromagnetic waves to achieve benefits go beyond what is possible with the conventional materials. You see, as we know that Snell's law says that light goes from rarer to denser medium, it bends towards its normal. That is the Snell's law or law of refraction. But in the case of our first diagram showing that the light goes from air to water, it bends towards its normal. That is the way. But in the case of negative refractive index, you see that this is also going, the totally negative refraction breaks the light waves reversely to the standard physics postulates. So this effect is one seen in figure on right, can achieved with the property designed metamaterial. This is the one. So you see, this is the pump with some clock. You see here, this is hiding one this way. These material impact the way electromagnetic waves through the substance. So when it is falling on it is reflected in such a way that you see that when you are when you are looking very intensified way, you can see that it is going in the reverse direction. This one. So in this one, this is the strongest effect noticeable, with the sense that the audience is still able to touch, hear the objects. That is also using that one. You see, this is going, and how that is S vector is going this one, this is going this directions. This is called chiral. So the metamaterials are artificial structures having unusual physical properties that are not available in naturally occurring materials, such as negative permeability or negative index of refraction. So these unusual properties may come from the strong interaction of waves with the internal elements that compose the structure, not because of chemical structure, only because of that physically modified structure. The above demonstration is an example of our research work showing a Gaussian beam incident from vacuum onto a sterile medium. For illustrating negative refraction and a backward wave. So this is the things how that the scientists have prepared the negative index metamaterial array configurations. So which was constructed of copper splitting rings, and the wires are mounted on interlocking sheets of fiberglass circuit board. You see that the total array of such a assemblies is only by the size of what is that, 10 mm by 100 mm by 100 mm. So you see that one, using that transformation optics, so we can describe the capability of bending of light or electromagnetic waves and the energy in any preferred or desired fashion for a desired applications. So this is the important ones. This transformation optics is a branch of optics which applies metamaterial to produce spatial variations. So derived from coordinate transformations which can direct chosen bandwidth of electromagnetic radiation. This is important one, how that light goes from source to optical system to detector. So this transformation of functions involved, like optical transfer function, then the modulation transfer function, another, the finally we reached to some energy encircled systems or spot analysis. So this is also important one. We can see that the principle of surface plasmon resonance. Here, this surface plasmon resonance for real-time interaction analysis for molecular array structures. So in this way, that SPR is main when you are taking the time versus responses. So when your association and dissociation involved, so in that we can find that how strong the interaction of how far or slow does the complex form and decay. Finally, how much of given molecule is active and how specific interaction taking place. So this high quality data can be used for identifying that microfluidic systems. So this is the light used as a laser. So when you are talking about the change in refractive index, we can find the refractive index changes by graphical representation. We can identify that sensing applications. So this principle of surface plasmon is important role in the case of, you see here, this is the glass substrate. Here in most applications, gold film is used in the top of that interface, and the hydrophils are introduced. So when that, the next slide, you can easily understand that how this kind of ligands, analyte, and other way of understanding of this surface plasmon resonance things can be used as a ligand injected into that other side of this one. So this is the curved surface. When the light is, laser light is falling on that, the total internal reflections is placing the major role. When I introduce some sample or that molecules, when the surface plasmons are produced, resonance taking place. So this the interaction taking place with this one. So the light intensity reflected from the lasers. So that total internal reflection taking place. So the variation in the refractive index making altering the changing of angle of incident. The SPR angle is proportional to that. So how much of binding taking place with this one association and dissociation graph showing that how much of interaction taking place with this one. So another slides may also giving that, that's one. So here this concerns of this oscillations or the plasmonic studies, so that the plasmonic materials that exhibits negative real permittivity. Most common plasmonic materials are gold and silver. However, many other materials show metal-like optical properties in specific wavelength range. So here, this is also one important one. Surface plasma. When a photon of incident light hits the metal surface, like the gold surface at the certain angle of incidence, the portion of light energy couples through the metal coating with the electrons in the metal surface layer, which then move to excitations. So this, the refractive index variation, showing that how the surface enhanced plasma technique. So that the oscillation making that the surface waves, so that the right now that light falling on that interface, that when you are changing the shift in registered real time, the whole antibody will move in such a way that for understanding of many experimental evidence showing that how that binding and taking place. This one here, the what we have seen from that animations, it is given in such a way that, so these are all the some ligand and the touchstone and the metal surface. This is the prisms like the curved one. This is the laser light. So when it is falling on the interface, the surface plasmons are produced. It is the plasma waves. So when you are introducing some samples within that input and output way, when your total internal reflections making this with the interaction of light and material matter, so the refractive index also changed. So in this way, the wave is on the boundary of the conductor and the external medium like air or water or vacuum, whatever it is. These oscillations are very sensitive to any change of boundary, such as the absorption of molecules to the conducting surface. So this is the things which are showing that, which you have seen from that animations, how we can go for the plasmonic waves produced and changing the direction of angle of incident. So this is the things, the main reason for using the prism here is to provide that evanescent wave. Evanescent field is nothing but the surface wave is called evanescent waves. So it is via total internal reflections that excites the plasmons in a metal flame. This is coated on the base of the prisms. So this is all the experimental setup of surface plasmon resonance. It is the collective oscillation of conduction band electrons that will produce energetic plasmonic electrons through the non-radiating excitons. This is the gold flames. This is the sample passed through that one, and the outlet is in such a way that some of the experimentalists doing in the curved path here. This is the triangle shape prism is used. Through that, we can analyze CCD camera how much of refractive index changes. So for that, we need to understand that how when you are changing that refractive index, surface plasma resonance (SPR). This is the optical powerful technique for identifying the biomolecules. So here it is used in many applications like life science, electrochemistry, gas phase, food and environment, and also in that metal optics. So here that gold sensor as a chip used here. Sometimes this is the curved prism is used. This is light from the laser light is going on. So to that interaction taking place, the interface making the plasmonic waves. So when you are changing the angle of incidence, so it can be moving from one direction to another directions. From the graphical representations, we can identify that how that the SPR oscillations in between metal and dielectrics. So these are all the process taking place. So this is the our experimental studies. We have designed in such a way that the stacked that is AU, MS, O2, nickel, graphene, and sensing mediums with varying thicknesses. So it is designed a new sensing configuration consists of two-dimensional materials. So silver and magnetic materials like nickel. Here the 2D materials such as graphene and molybdenum sulfide are employed to improve the light absorption capability of sensing applications, which are much beneficial to get higher sensitivity. So the reflectance curve, resonance angle, sensitive or analyzed theoretically using Fresnel equations. Using that some transformation matrix method. So the results show that the addition of materials such as MoS2 and graphene on magnetic material, nickel, shows a higher sensitivity than the traditional sensor experimentals. So these are all our experimental, theoretical background, how we have used AU and nickel. With that, this one our paper published in journal. I will show it later. So this is the things when you are taking graph between incident angle and reflecting intensity. So you see that for different layers of options of this one. So the next slides also showing that how that different changes in the refractive index of sensing medium. And similarly, you see that the sensitivity comparison of different reported prism based SPR biosensor. So here, there are many of them used different configurations, but our proposed systems used this one, AU, MoS2, nickel and graphene. We obtained the sensitivity of 229 RIU, refractive index unit. So we observe that the proposed sensor exhibits enhanced sensitivity compared to the conventional gold film based SPR sensors. So this is the AG nickel biometallic film on CAF2 prisms for high sensitivity surface plasma resonators. So this paper appeared in Optics and Quantum Electronics. So this is also the same method we have, that the polarized light like laser light. So when it is reflected by the total internal reflections, we have selected CAF2, AG, nickel and sensing mediums. So this SPR sensor would find a new platform for medical diagnosis, chemical examination and biological samples detections. So these are all the things we can draw the graph between thickness of different layers with the minimum reflectance. These are all the sensitivity versus thicknesses, and also this thickness of edge layer with the nickel. How that refractive index changes, sensitivity also, that the reflectance also changes. So these are all the data showing that our experimental evidence says that our proposed values, the sensitivity we achieved 504 times refractive index unit using our one. So this SPR biosensor utilizing a biometallic layer of AG nickel on a CAF2 prism is numerically studied. The result show that the proposed sensor can enhance the sensitivity as high as 504 degree per refractive index unit, and can still keep the full width half maximum of resonance curve as low as 4.85 and hence enhance the quality factor as high as 103.9 per refractive index unit. So it is believed that such a structure with the favorable results will make the proposed sensor an appropriate and a potential candidate for recognized biomolecules, organic elements, and other samples. You see that This is the graph between incident and the reflect. So when you're introducing the many layers, how that refractive index changes is the important one. So based on our one uh, software that is called ZMax, there are different types of configurations available in that one. It is sequential ray tracing method, non-sequential ray tracing method, and also that engineering version, scientific version. Many applications are available using that ZMax actors. So for that, the total residual degree of polarization on the detector plane can be identified, and also the intensity distribution on any plane along the optics axis also can be detected. So this residual polarization profiles on any plane along the optics axis is also identified. So this is also how we can identify that sequential ray tracing or non-sequential ray tracing method using that ZMax approach. So this is that different types of mesh structures are introduced for hiding that samples. So this kind of metamaterial applications also important. Here we see that different mesh structures, that is meander structure, double meander structures, everything. So this profile indicates that the significant residual polarization left on the detector plane. So this starts from some incident angle from greater than 100, then 40 to 50 degree, and also that significant role plays in 20 degree. So this coupling of polarized light into unpolarized light is associated with the reduction of degrees of polarizations. You see many applications involved in that metamaterial. So here this is splittering and clocking. We can clock the image. This is the hydrotropic metamaterials. So these are all the super lens metamaterials. So this is also a things which is called optical nano antennas. And this is the plasmonic sensors. These are all the applications of metamaterials. Even that double negative metamaterials, electromagnetic band gap, then artificial complex ground plates. So these are all the band gap metamaterial filters, then epsilon band gap materials. So everything is possible by the metamaterial. These are all the application side. The metamaterial is used in many applications, like the second slide will be important. That is modified properties of metamaterials. Using that field of mechanical engineering, then acoustical engineering, then optical engineering, even electrical engineering, transporting engineering, thermal engineering, everything is plays a major role in metamaterials. So this metamaterials also involve that hiding the things. Where I will show you the next slide, which is used for airports for checking security checkings, so that we can see that how the light bending from its direct way. So deviation from its original path is also using that metamaterials. This is metamaterial solutions. So this is the things we can use that metamaterial as a super lens. This can be engineered in microscope. So we can see that on the perfect identified. This is the diffraction free one, this one. So that the diffraction limit can be identified and it delivers the image resolutions beyond that conventional microscope. So this type of super lens enables participants to explore unseen objects, particularly in the nanostructured elements can be identified using that metamaterial super lens. So you see that one fellow is entering into that security inspection in the airport. He stands directly in front of the neuro metamaterial walls, which is fabricated from inhomogeneous metamaterials. Under the electromagnetic wave illuminations, the wall performs the entire image processing and provides the result of inspection of electromaterials. He is having some gun in the pocket. So it is the perception result is identified using this. The gun hidden at the wrist will induce distinct scattering waves that will propagate and scatter further inside the wall and are translated directly to a warning signal at the customer interface. So these are all, this is the very important ones. So when you are considering many monuments, that the old buildings, very precise and very valuable buildings can be protected by metamaterials. So if this building collapse is the primary cause of earthquake related casualties. So with an average of over 8 earthquakes with more than 8 Richter scale with the magnitude, so that globally architects and engineers are constantly looking for better way of reducing the impact of seismic waves or earthquake waves on the structure integrity of buildings. So the scientists developed a seismic metamaterial capable of attenuating seismic surface waves between 0.5 and 22 Hz, covering the resonance frequency range of most human-made structures. So already I told you that it will react that seismic waves and protect the building. So this, when partially buried in the ground, encircling the building, the material isolates seismic waves that can cause resonance. So automatically the reverse resonance protect that surface waves. So the protected buildings during the earthquake will save and may not feel vibration at all. This is the peculiar and important applications of metamaterials. So this seismic metamaterials not only protect new buildings but also protect ancient buildings, because it does not need to change the original structure of the protected objects. So the material is made up of a series of seismic metamaterial plates formed by horizontally arranging resonance elements, which are then placed atop a solid substance to test its damping capabilities. The group compared the impact of seismic waves with and without interaction with the metamaterials and found the material effectively blocks the earthquake waves transmissions. So the large scale test and improved manufacturing techniques are needed before applying the seismic metamaterials to realize to real life structures. So it holds promise in protecting vulnerable buildings and metropolis with this simple designs. So the scientist hopes that it will eventually be used as a replacement of conventional isolation methods. So these are all the results obtained from our work. So these are our conclusion that what metamaterials, how it existing, and how it can be used for many applications. So these are all the materials of composed macroscopic structure, so that achieve a desired electromagnetic response can be referred to as a metamaterials. Almost all agree the metamaterials do not rely on chemically or atomic alterations, only because of the structural modifications. So these are all the conclusions. Plasmonic metamaterials, how the plasmonic metamaterials are silica coated gold, that is AU nano cubes, AU and AG core shells, zinc and copper. The idea is that AU and nanoparticles will improve electron transfer in conjunction with the plasmonic and scattering effect. So that the theory behind that one is proposed by Victor Veselasco and a Russian scientist in the year 1965, also known as left-handed or negative index metamaterials. So Veselasco theoretically identified that it would exhibit optical properties opposite to that of glass or air. So the design is important along with the analysis and applications. In this way, the control of optical properties of nanoscale and integration of different components remains one of the hardest challenges. Nevertheless, the progress made in metamaterials over a relatively short period of time is phenomenal. So the realization of full potential of this new class of metamaterials will have a profound impact on several disciplines, including electronics, communications, medical diagnostics, healthcare, and manufacturing industry. So the demonstration of novel functionalities and applications at the research scale is only the beginning of the road for metamaterials. So these are all our papers appeared in different journals. So these are all my research scholars. There are 25 research scholars. They have completed, all are well settled. That is our heartfelt thanks to God. They all settled well, having its many higher posts. So these are all the 25 students. So these are all the listed our scholars. They are well settled in different concerns. So thank you very much. Thank you for the attention. Thank you very much, Professor.
Well, Professor Anbarasan, I would like to acknowledge you once again, your courtesy, your friendship, and all the knowledge you have exchanged with us and share with us. Thank you very much indeed. And please stay safe, and we are more than happy to have you around. And I wish you the very best on luck and success. And the more important thing is that I wish you happiness for you to carry on doing this lovely piece of work. What you have done is wonderful, and I think you are going to do better and better. Professor, thank you very much indeed. My regard to everybody, and all my love to India. Bye-bye, Professor.
Thank you. Thank you. Good night.
Bye, my friend.
Okay, thank you, Professor. May I wind
Bye.
this section?
We
May I
are
wind this
now.
section? Any questions?
Pardon? No,
May,
you will get all the questions by email,
yes, certainly.
and
Extremely.
this is the best way. Otherwise, your talk is going to be disturbed by many questions and people like that. It's better to have the clear talk, and then people can ask you directly. Okay?
Thank you.
Thank you very much indeed. And God bless you. And
Thank you.
bye-bye.
Thank you.
Bye, my friend.
Bye bye. See you. See you.